Welcome to Way Happy Studios, coming from the northern studios of Way Happy. This is Mr. Meyer, and this is 7.5 in another section that you are just going to say, wow, I love Chapter 7. It's because it's going to talk about graphing inequalities, solving systems of inequalities, and linear programming problems. And so let's get right into it. When you graph an inequality, the only difference is that there is actually an inequality. And what's important about that is you have to decide if you use a dashed curve or a solid curve, and that will tell you by the symbol. If it's less than or equal to, the equal to part is the important part. That's when you do a solid line. If it's just less than or greater than, you use a dashed line. Also, you will test at least one point, and you will see if that point is in your solution area or not. And if it is, you shade that side of the line. So with enough being said, let us go ahead and try to draw a graph or two. So notice this very first one here I am going to graph this equation right here. And so on my graph paper, I will start off with the positive 4 because it's a line. So 1, 2, 3, 4, dot. And then the slope is 2. That means up 2 over 1. Now the new part, I'm going to have to decide if I want a solid or dotted line. Notice it is solid. So we will draw a solid line through those 2 points. And now all we have to do is test. And so I will test the point 0, 0. Only key here is that you need to test a point that is not on your line. So I know that the point 0, 0 is not on the line because I can see it. So I will test it. So I just plug it in. I get 0 is less than or equal to 2 times 0 plus 4. Or most of us know that that is less than 4. And we say, hey, that is a true statement. So just make sure the point you tested, if it's true, make sure it's in the shaded region. If it's false, make sure it's not in the shaded region. And you are finished. So there it is, a shaded region. Done. All right, well, let's crank it up a little bit. What about if it's a system? So you might have a system of 2 equations. Oh, very scary. Not really. Graph both of them and then tell me the overlapping region that is the solution to this. So again, I will go ahead and graph this. So we'll get my graph paper out and I will have to draw a grid on here. And so there's my grid. And so to graph that first one, now I'll do it a little differently because the equation's written differently. Instead of knowing the slope and the intercept, which I could find, I like to use just the intercepts. So first thing I would do is pretend y is 0, and I would say x is 2, and I put a big old dot. And then I got to go back and pretend x is 0, and I get y as yuck, 4/3 or 1 1/3, and boom, there it is. And notice this time it is a dashed line, so I will dash this bad boy. And I could test now a shaded region less than, so I'll test 0, 0. Y x 0 is less than 4 is true, so I will shade below. And here, for the oohs and ah factor, I will shade the region with a highlighter. So, ooh, that looks so pretty, right? I know, jealousy surrounds you. But there it is. I have the shaded region. Now I will graph our other graph, which is a parabola. And it's opening up and it's not shifted, so this is kind of nice. It's going to start right here at the origin. It's going to go up 1 over 1 on both sides. And voila, I have a gorgeous parabola. Oh, did you catch my mistake? Should have been dashed. So dashed line. Again, I haven't really checked the next points very well, but it's good enough for me. And there it is. And now what I want to do for this dashed line is I now want to test a shaded region. So again, I will test the point. Ooh, I can't do 0, 0. So maybe a little trickier. I will test one that I know is either inside the parabola or not. I will pick the point, I don't know, way up here. 0, 10 is my tester. And so I will put in a 10 for y, a 0 in for x, and notice that is definitely true. 10 is greater than 0, so I need to shade above. And so I will take another highlighter for effect, and I will shade above or inside the parabola. And notice the overlapping region of a yellow and a blue highlighter made green. What? So the green region is our actual solution, right? Our actual solution is everything inside the green region. Solution area. Anything you pick in there that is not on one of the dotted lines but is inside that area is a winner, and you have now solved a system. So why don't you give it a try, and I will see in a minute what else I can show you. Excellent work. And now, what could be more exciting than that? Well, how about some linear programming? So oohs and ahs, linear programming is usually when we take real life problems, we make a set of constraints, which we have to graph, just like you did in the last problem. We'll get a feasible region. We will then find the vertices of that feasible region, so all the corner points, and we will plug the corner points into what is called the objective function, which usually they will try to maximize or minimize, depending on what we're trying to do. If we're trying to maximize our profits for our company, we would want to maximize the objective function. If we're trying to minimize the cost of our company, we would want to minimize the objective function. So there's usually some reason you're doing this, and that's your objective function, to make money, to lower cost, whatever. Again, it all starts off with a beautiful graph. So here's my graph, and I'm looking at my constraints. Those are the things that I will be graphing, and I'm noticing that x is greater than 0, y is greater than 0, 1, which really tells me I'm only going to be in quadrant 1. So I didn't even need the other parts, but I got them anyway. All right, let's graph that first one. If I cover up the x's, I get y is 10, so 2, 4, 6, 8, 10. So there's 1 point right there. And if I cover up the y, I get x is 5, so there is 5. And now I'm a little nervous about how straight my line will be, so I will just draw a straight line right through it. And everybody can say, what? Beautiful. Again, the line would actually continue up higher to the left, but I didn't really care for that. Shade it. Let's see, 0, I'm trying to test 0, 0. 0 is less than 10, so everything below would be shaded, and life is good. And the first one's done. What about the second guy? So let's graph the second guy. Cover up the x's, and you get y is 14 thirds. So what is that? 4 2/3. So 4 2/3 about yay. And then I'm going to cover up the y, and I get x is 7. So that was 5. This is 7. And again, I will make a beautiful line through those 2 points. And hopefully I will now be able to shade everything less than that, because it's 0, 0 works. So everything less than that is shaded, and we get our gorgeous region. Oh, should have paid attention to this. X is greater than 0 means everybody to the right. Y is greater than 0 means everybody above the x-axis. And here now is our feasible region. All solutions in that region, or due to our constraints, we have machinery hours or whatever, we have people's work hours, everything that we constrains our business, there it is graphed, and we can produce however many widgets we want as long as it's in that feasible region. And now I just need to find the corners of this feasible region, and those are usually the extreme values of one thing or another. And so as you can see, this one up here was 0, 4 2/3. For math reasons, I might want to call that 14 thirds. The origin was 1. So if you want, I'll throw the origin on there, which is 0, 0. This guy right here looks like 4, 2 on my graph. Or I could use systems of equations and solve this to find out exactly where it is. I know it's 4, 2. And then the last one down here is 5, 0. And so now all I have to do is figure out which one of those will give us our maximum value and our minimum. And so I plug it into the equation. So again, going into our objective function, which is the whole reason we do this problem, I would plug in our x and our y. Here's probably where I would want 14 thirds. And I get negative 56 thirds when I value that. So that's pretty small. So that's a pretty good minimum already. How about 5 times 0 minus 4 times 0? When I check the origin, that gets me 0. I'll plug in 4, 2, which is 5 times 4 minus 4 times 2, which is 20 minus 8, or 12. And last but not least, 5 times 5 minus 4 times nothing. That gets me 25. And there you have it. We just found the maximum. We noticed the minimum off the start, but we had to check everybody. And so there's our minimum value. There's our maximum value. life is good. Now, these are usually a little harder when you have to come up with the constraints yourself, word problem type things. So we will enjoy those. But have a great day. Stay happy. And I'll see you tomorrow.